Now we can look at actually implementing this feedback controller on that same plant we were investigating before. So again, the plant or the open loop system, that circuit is the 1 over 2.5s plus 1. Remembering back, we want the voltage across the capacitor to be 5 volts. Ideally, it goes from 0 to 5 instantly. We're going to see that's not really something we can achieve, but if we get the steady state value of it to be 5, we're going to typically be happy. So that's our G naught, or our plant. So that is the outlined in green part on this feedback controller. So again, we're not going to change anything about that original circuit. We're not changing the resistor or the capacitor in any way. We are just going to be changing what the input is into this circuit. So what we get to choose in our design is going to be outlined in yellow here, just what gain do we want on that controller. So first let's look at a little bit of the math of what is the output of this system going to look like, the E out, since that again is ultimately what needs to be 5 volts. So instead of just looking at the transfer function as E out over E in, like we were before, and that still is that G naught, what we're really looking at is, since we are sending in this reference signal of a step function of 0 to 5 volts constant, we want to look at really what is the closed loop system's transfer function. What does E naught over R look like? That's the transfer function that we care about. If we feed in R as a 5 volt step function, what does E out look like in this feedback system? All right, so we know from before in block diagrams when we were looking at feedback systems that this is going to be what the closed loop transfer function looks like. So it's this kg naught over kg naught plus 1. Again, we can rederive this, but that is going to be the transfer function for the closed loop system. If we actually go through and we put in the 1 over 2.5s plus 1 in the numerator and the denominator, and then we just clean it up a little, clean the algebra up, then this is our closed loop transfer function, is this k over 2.5s plus 1 plus k. And in all of our systems, we are going to keep our gain k and any gains we have constant. In principle, they could change in time. That's out of the scope of what we're going to look at in this course. And when we're talking about feedback control, the transfer function we really are concerned about is this one, the E naught over R. The open loop one is still involved because we see to get this closed loop transfer function takes the open loop transfer function, but it's modifying it. So effectively, this is the new transfer function for our system. We built this apparatus around it, and now we want to see how does this transfer function behave. Well, it's going to behave in a similar way to our open loop one. It's still first order, which is not necessarily the case. We're going to see ones where the order of the closed loop transfer function is higher, but this one is still first order, so it's still going to behave like a first order system. However, we're going to see that we have some options here. If we look now at the time constant of our closed loop system, well, we have a 1 plus k as the constant, so really everything needs to be divided by that 1 plus k. So what's going to happen, the 2.5 is going to get divided by the 1 plus k so that we can get it into that standard form. So if we do that algebra, we get it into the standard form so that we can sketch and talk about a first order system. We get that the time constant is now 2.5 over 1 plus k. So what does this let us do? From what we know about a first order system, the smaller tau is, the quicker generally we're going to get to our steady state value. And then if the tau is bigger, it takes more time to get to our steady state value. So since we get to choose what the gain is in the system, how much we amplify in this error, we get to choose this k. And as a side note, k must be positive in the systems we're looking at. So we can choose any positive value of k to put in there. So if we look at what's happening, the bigger k is, the smaller tau is going to be, because k is in the denominator by this calculation here. So we can get our system to respond faster by choosing a large value of k, by putting a lot of high gain in our system. All right, so we know from what we know about first order systems, that's what's going to happen. Let's again look at the math of not only how fast is it going to respond, but we also want to look at what is the final value going to be. And to see what the steady state value or final value is going to be, we can use final value theorem on this. So we have a stable system here. Our S is going to be in the left half plane. The one pole is in the left half plane for our system. So we're okay on that front. So we can apply final value theorem. But we want the final value theorem on E naught because we want to know what does the output voltage look like as time goes to infinity. So I'm not doing the final value theorem on the closed loop transfer function itself. I do need to multiply by R so that I have E naught just by itself. So I took this equation and I multiplied left side and right side by R. So remember, final value theorem is we can know what happens as time goes to infinity in the time domain if we look in the frequency domain as S goes to 0 of S times our function. So that's what I'm doing here. I'm taking E naught, I multiply it by S and let S go to 0, just like we saw before with final value theorem. So on the right hand side, I have R times this K over 2.5S plus 1 plus K, so that the left side had only E naught, and I have that S that also carries over. Right, so I can look at SR times that K over 2.5S plus 1 plus K function. Now, in this system, my reference is, again, what do I want my output to look like? I want it to look like a step function with an amplitude of 5 volts. So, capital R is going to be, well, the Laplace transform of that 5 volt step function. So that's going to be 5 over S. Right, so R becomes the 5 over S. I have the S over here. So we're going to see that those two S's are going to cancel each other out in this calculation. So now I can evaluate my function when S goes to 0, or in this case, S equals 0. I don't have to do anything fancier with the limit. So I'm going to get 5K over that 2.5S term is just 0 over 1 plus K. All right, so if we go through all the algebra, this is telling us that as time goes to infinity, the output voltage is going to be equal to 5K over 1 plus K. So we have a problem here, or we're going to see it's a problem, is that the output voltage is dependent on the gain that I choose. So let's say I choose a very small gain. Let's just, for simplicity, say I make K equal to 1, relatively small. Well, then I'm going to have 5 times 1 is 5 on top, and 1 plus 1, 2 on the bottom. So I get 5 over 2. So this is telling me as time goes to infinity, my output voltage is only going to be 2.5 volts. However, my desire is that it's 5 volts. So if I try a higher value of K, a higher gain, let's say K is 10. So if I do that, I have 50 over 11. Well, that's still less than, it's a little bit less than 5, but it's closer to 5. And if I choose an even higher gain, like 100, I'll get 500 over 101. Again, it's pretty close to 5, but still a little bit less than 5. The problem we're going to see when we simulate this for this particular system is that no matter what gain I choose, I am not going to get my output to be that desired 5 volts. I can get close, or I can get closer and closer, but it's going to require a higher and higher gain to do so. In general, when we see a steady state value like this with a K with gains in it, that's probably not a good controller, and we'll address that in the next subsection, but we'll see in simulation what does this translate to. So in general, analytically, before we get to simulation, the higher the value of the K we choose, the faster the system will respond because our time constant will get smaller, and the higher K we choose, our steady state voltage is going to approach 5 volts, but not do it. So a downside of this controller right now is we're not going to get exactly the output at steady state that we want. However, with higher gains, it will at least respond faster. I'll also note for this system, if we look at the schematic picture here, we don't see an actuator or a sensor. One, this is purely electric, it's already an electric signal, so we don't need to go from a mechanical signal to a electrical or vice versa. And what we're going to see is that for really all the systems we talk about, we're going to assume the actuator just has a transfer function of 1 and the sensor has a transfer function of 1. It's not necessarily a great assumption. As we saw from the end of Unit 2 when we're talking about sensors, sensors themselves might be first order, second order systems and have a time lag, and actuators the same way. If we include those in our system, really what it's going to do is be modifying what our closed loop transfer function is, and we can still accommodate that, but it's going to be more difficult than we want to get to in this introduction to control. So just be aware the sensor and the actuator in general will contribute to the closed loop transfer function. We will ignore them though for now. So next we can validate what we're finding in simulation. Again, we already know analytically what should be happening. Let's simulate this and make sure we're seeing the same thing. So we can go into MATLAB, and I'm going to do the simulation here in Simulink. So bring up the Simulink model for our proportional controller. This is what it looks like. So we have our open loop transfer function, or the plant that was given to us. Again, we're not modifying that at all. My reference signal here, if I go into it, we see I have, it starts at 0 and it has a final value of 5. This is a 5-unit step function that I'm putting into my system. All right, so that step is going in. We have this summation happening. Out of our plant, we have that E out, just like in the picture. That is coming down, and that's feeding into the negative side of this junction here. So out of that junction is the error. That error is going to get multiplied by this quantity Kp. That becomes EI, the input into my circuit, and it's going to act just like it does on the slide. So what I want to do going into MATLAB is I'm going to take these 4 signals, the reference signal on top, the output signal from my plant, the input that goes into my plant, and what my error is. I'm going to output all of those into MATLAB as I run this simulation. And I'll do this over 5 seconds for this demonstration. Do notice here, Kp, it's in red right now. I'm going to define its value in MATLAB, and once it's defined, this won't be red anymore. But this way I can quickly change what gain I want to use. So I'll run this through MATLAB, and first I'm going to try, like I discussed before, what if the gain is just 1? So I'll set my Kp equal to 1. I'll run my sim in 35. So once Kp is set, it's going to run my exact schematic with a gain of 1. And then, like we saw before out of Simulink, we're going to get this sim out, and I'm going to kind of part it out because I know what each column of sim out data is going to be. Once again, it comes out in the same order. Each column is in order as this concatenate is vertically. So in my schematic, I did write it out here to remind me. First column will be R, E out is second, EI is third, and the error is fourth. And it's the same as reflected in the MATLAB. And I'm going to plot all 4 of those signals simultaneously. All right, so I'm going to run this. And this is my result when Kp is 1. All right, so the reference in all of these is just going to be a constant 5 volts because that's what we want the output to look like. The second subplot here, that's what the output actually looks like. So I can put on my tracker here. So we see as we get to 5 seconds, as predicted analytically, since we know how we used final value theorem, 5 seconds wasn't quite enough time, but we see as time goes on, the Y value is going to approach 2.5 volts, and that's exactly what we saw analytically before. Also, we can look at what does the input voltage look like. Again, because initially the error, well, we can see that below, the error is 5, and we're multiplying that by the gain to get our input voltage. The input voltage starts at 5 volts, and it's going to go down, and then asymptotically down to 2.5 volts using a gain of 1. And last part, we can look at the E out again. It is a first order system. Our closed loop system is first order. So if we look where the time constant is, that's going to be determining the response time. So this one is going to be slower to respond than subsequent tests we do. And we'll compare them all 3 examples at once in the end. So quickly, we'll see the difference. What if our gain is 2 instead of 1? Right, simulating this, we see that as that K increases, for this plant at least, the E out, that final value of our output voltage now is, it should be 3.33, 3 1/3. It should asymptotically approach. So we're closer to that 5 volts. We're clearly not there yet. Our reference didn't change, but our EI if we see what's happening there, now at time 0, we have to put 10 volts into the system. And then as time goes forward, we're going to reduce that down to a constant 5 volts going into 3.33 volts going into the system. So we did get closer to the 5 volts in our output that we desire. We're still not there yet, but we're paying a penalty, or a trade-off here is that initially, at least, we have to put a much higher voltage into the system, 10 volts. And we're going to see that the system is responding more quickly because that tau is getting smaller as k increases. So the response time, or the time constant of E out, is faster. And finally, what if we make k 10? All right, so we see here that the response of E out much quicker. These are all scaled the same x-axis, 5 seconds. So the response is much faster, much smaller time constant. And we see that the steady state value of the output goes to 4.55 or so. Again, still not that 5 volts that we're looking for. And on the downside is that it takes a peak voltage of 50 volts in the input. So what we're going to see is that to get these high gains so that our time constant is small and so that our steady state value is closer and closer to 5, it's going to take an enormous input voltage as that gain goes up, which means that we need something that can create that high voltage, and we have to look at the actual plant or circuit this is going into. Can it handle high voltages like this initially of like 50 volts to get the response that we want? So let's look at all 3 of these examples. I just picked, in this one I'm actually doing 1, 5, and 10 that we'll compare, but we could choose any k value we want to compare, but now we can see all at once how are they going to differ. I'm just looking at the input voltage and the output voltage right now because the reference is all the same, it's always 5, and then the error just is going to impact what the input voltage looks like. All right, so we have the black line is a gain of 1, red is 5, and green is 10. So the trend, as I was just discussing, continues as I increase, at least for these 3, as I increase my gain, that peak voltage required is increasing by that factor. So that's going to be definitely a downside. And if I look at the output voltage, that is good for us as the gain increases, that steady state value gets closer and closer to 5. All right, so overall, how did this proportional controller work for this plant? To control this plant to get to that steady state 5, really it didn't work in general because, as we saw from the final value theorem, no gain would make it 5 volts, would make the steady state output 5 volts. Because we had a k in there, it will never, we can get asymptotically closer, but we're not going to get to that 5 volts. So we can't drive the error to 0, which means, or that's also to say we can't get the steady state output to reach the desired output. Now I do want to caution or remind every time that is true for this particular plant, this 1 over 2.5s plus 1. There will be other plants where a proportional controller will work. When we apply final value theorem, we're not going to have any k in it. It's going to be exactly what we want it to be. For this particular plant, that was not the case though. So once again, we can drive it towards 0 error or towards a steady state value of 5 volts, but the downside is going to be it requires a very high gain, and we saw that on the input side into our circuit that at peak it's going to require a very high voltage to get that quicker performance by making the tau smaller and more accurate performance by making the steady state voltage closer and closer to 5. So we can improve the performance with higher gain, however the input voltage peak is very high to do so. So it's going to take more than just a proportion of the error in this system for this plant in order to control it fully, which is to say to drive that steady state error to 0 or get that constant, that steady state value of our output to 5 volts.